So yeah, I think we are ready for the start of this session. So first speaker is Jisan Song from Chungang University. She'll talk about flux mediated dark matter model. So please start.
Hi, I'm Jisan Song from Chungang University. Today, I'm going to talk about the dark matter interactions in the full-form flux model that explains the relaxation mechanism and the possibility that dark matter can be observed experimentally in this model. WIMP has strong limits from direct detection experiments such as xenon, but there are interesting excess or signatures for indirect detection in cosmic ray experiments such as AMS. Here we discuss the possibility of obtaining the observable signals for indirect detection, while satisfying the correct relic density and the strong constraints from xenon and the other bounds from collider searches. First, I will explain about the hierarchy problem. According to the effective theory, all physical quantities are associated with fundamental physical quantities, and in the standard model, all physical quantities are represented by the vacuum expectation value of the Higgs field. So theoretically, the vacuum expectation value of the Higgs field should be equal to the Planck mass. However, vacuum expectation value of the Higgs field is 10 to the 15 times smaller than the Planck mass. So the question why the Higgs boson is so much lighter than the Planck mass is the Higgs mass problem. Another problem is the cosmological problem. The cosmological constant is the fundamental constant for the energy density of a vacuum, and theoretically it can be predicted that the cosmological constant is above Planck mass. But the cosmological constant was measured 10 to the 120 times smaller than the Planck mass. The problem of explaining this is called the cosmological constant problem. Selfish Higgs was proposed to solve this Higgs mass problem. In this case, this mechanism is called selfish Higgs because Higgs acts as an entropic selector for the emergence of a fairly unique non-empty universe. The selfish Higgs is based on the standard model with addition of a single non-dynamical field described by a full-form. A full-form couples with the standard model and derives from a three-index antisymmetric tensor field. If we assume that the full-form starts in the early universe, in a highly excited state, this excited full-form can reduce its energy by creating membranes. In this process, the transition of the full-form configuration occurs. But in this scenario, the universe would appear empty at the end of the last membrane nucleation without a rating mechanism. So this is our model. With full-form flux, we consider Stoskala field phi for rating after the relaxation of the Higgs mass and the Dirac-Fermion dark matter chi. Both Stoskala phi and standard model Higgs have coupling with full-form flux, and dark matter chi is coupled with Stoskala phi. And there is a shift symmetry for the Stoskala field respected by the full-form coupling, but it is broken by the mass term. Since the commutator has direct coupling to the source scalar field, we can communicate between the commutator and the standard model particles only through the Fulton couplings. Using the equation of motion for Fulton field, Lagrangian becomes this equation. Then the effective Higgs mass and the effective cosmological constant are given by this, and both depends on the flux parameter Q. And using the equation of motion for antisymmetric tensor field, we can quantize the flux parameter Q in units of E. Whenever we nucleate the membrane, we can decrease the flux parameter Q by 1 unit. This flux change stops at Q equals Qc minus E, with Qc is the value of Q when the effective Higgs mass is 0. It is due to the exponentially suppressed tunneling rate from a small cosmological constant to a negative cosmological constant. As a result, the effective Higgs mass and the effective cosmological constant are relaxed to the two true values at the same time. Can you hear me?
Yes, we
Yes,
can.
no problem. Yeah.
My internet is
Please go. No problem at all.
my screen is stopped.
Oh,
Oh, I don't know what's the problem. Sorry.
yeah. Please stop the screen sharing and then restart. Jisun, please rejoin again. Yeah. Yeah. The possible solution is quit your Zoom and restart. Yeah, that will be better. Okay.
Oh, can you see my screen?
Yes.
I'm sorry.
Okay. Yep. Okay.
Oh, let me start.
Yeah, please go ahead.
And we extend the standard model Higgs and the source scala around the vacuum. And since the source scala phi and the standard model Higgs is coupling with the proton flux simultaneously, it can be transformed to the less eigenstate H1 and H2. Here the mixing angle theta depends on the cross parameter Q. Because the electric symmetry is broken at Q equals 2C minus E using these values, just after the last membrane nucleation, the vacuum expectation depth value of the source scalar field is shifted by the proton flux. And the source scalar field starts oscillating from the shifted value, so the rating occurs. Using this initial vacuum energy, we can calculate the maximum temperature of the universe after the inflation. Then choosing the value of E, we get the maximum temperature from 40 GeV to the 4 keV. Then for the dark matter mass is smaller than the maximum temperature, dark matter starts being relativistic and in equilibrium. From here, it's about the interaction of dark matter. Because of the vacuum expectation value of the source scalar field, the less term of the dark matter is shifted, so we redefine the dark matter. And in the basis of the less eigenstate for the scalar field, we obtain the interaction terms for dark matter here. And you got couplings between the standard model and the standard model fermions becomes this equation. Yes. For the proton coupling, the scalar field has CPO and Higgs field has CP even, so this leads to the CP violation. From this, the dialectic question of the dark matter has CPO coupling like this, so due to the chiral operator gamma 5 in the mediator coupling for dark matter, the direct detection cross-section for fermion dark matter is suppressed by the momentum transfer between dark matter and nucleon. However, in the dark matter annihilation process, unsuppressed exists, and because of the mixing induced by the proton flux, dark matter can annihilate into the standard model fermi. Can I re-share my screen?
Okay.
Oh,
Is there
I'm
any
very
problem?
sorry. Let me start. We consider the thermometer with a smaller mass than the maximum temperature in the reacting process. In this case, the thermometer can pair annihilate into a pair of the standard model burner, and this is the S wave. So this is relevant for indirect detection. Also, if the thermometer is other than the mass of H1 and H2, the thermometer can annihilate into these particles. Or the processor suppressed by the small cylinder, but unsuppressed can exist in the P-wave in the process that the thermometer annihilate into H1 and H2. This is for the direct detection. And as I said before, elastic scattering between the thermometer and neutrons or electrons are suppressed because the time delta is small value. We found that the Warner correction in direct detection can be feasible when the source color has only gamma 5 coupling to the connector. So we are working in progress for this. This is the result. The correct air density is satisfied on the red line, and the gray region is excluded by the direct detection from gamma momentum, which is the connector and nuclear scattering. Green region is excluded by the Higgs search at black, and purple region is disfavored by diffuse gamma rays from Fermi-Lab galaxies for the without annihilation channel. Blue region is favored to explain the AMS and superphoton effect, but there is no consistent region to explain the Fermi-Lab gamma ray excess at the galaxy center because of the bounce from Fermi-Lab galaxies. This picture is the same as the previous one. The red line is red density and gray and green region is excluded by gamma momentum and black. And purple region is disfavored by diffuse gamma rays from Fermi-Lab galaxies. Orange region is found from Higgs invisible decay. To summary, we consider the photon flux model. In photon flux model, a simultaneous relaxation of the Higgs gas and cosmological constant is possible. In this case, effective Higgs mass and effective cosmological constant depend on the cross-electric field. And we consider the stokes-Scalar field to explain the reacting process. In this scenario, we introduce Dirac-Brownian connector with two-scalar coupling. Here, flux profile leads to mixing between stokes-Scalar and Higgs. So direct detection for the connector is suppressed, and in indirect detection, unsuppressed can exist, so we can explain the signatures for passing waves. Thank you.
Okay, thank you for the talk. Yeah, actually, yeah, time is over, but yeah, if you have any very urgent question, we can have, yeah, one. So if any urgent question, if not, yeah, we'll move on to the next schedule. So is there any other question? Okay. Yeah, if not, yeah, we'd better move on to the next schedule. Yeah, due to very tight schedule. So yeah, thank you. And then next case, Papeng Huang. So are you ready?
Yeah, I'm ready. Can you hear me?
Okay, so yeah, you can show your screen and please use the full screen.
Okay. Screen. Can you see in the full screen?
Yeah, that's great. So next speaker is Professor Papeng Huang. He'll talk about exploring the light dark matter by SKA set. Yeah, please start.
Okay. Good afternoon. Thanks for your attention and thanks for the organizer, CTPU IBS. I really feel glad to virtually go back to CTPU. I once worked here from 2017 to 2019. And today I will introduce the new idea to explore light dark matter by SK-like experiments, which is based on the following 3 papers with John New, Hypon, and Rachel, James, Pupo, Francisco, Kenji, Tuakazu, and Tashino. And the original idea is based on the work when I was in IBS with Kenji. This outline my talk. First, I will introduce my research motivations, and I will discuss how to explore light axion dark matter and light dark bottom dark matter by SK. The last is a simple conclusion. Whenever we see this cosmic pi, we're always confused what's the nature of dark matter. A lot of experiments have been done to unravel this long-standing problem, but the current experiment like LC and dark matter direct search didn't find any expected signals. The current situation may point us towards new ways to understand or search in dark matter. Today, I will introduce using the radio telescope to search for very light dark matter, as light as micro EV or even lighter. What is dark matter? Nobody knows, but we have many observations like galaxy rotation curve, bullet class collision, CMB spectrum, gravitational lensing. But probably we want to find some new experiments we can provide a new idea to understand the light dark matter. Fortunately, we have and will have the SK. SK has very high sensitivity up to sub-microjansky, and we also have the 500-meter radio telescope in China and GBT USA. First, I will review the previous work with in IBS with Kenji. Let's talk about how we can explore the light axion dark matter by SK. As axion dark particle, as you know, is well motivated from the strong CP problem or string theory. It is still one of the most attractive and promising candidate. We study how to use the SK-like experiment to observe the radio signals from the resonant conversion of axion cold dark matter from the magnetized astrophysical objects like neutron star or white dwarf. The basic picture is shown here, showing the dark matter is composed of non-relativistic axion or axion-like particles. This is a neutron star that is very dense. The mass is about 1 to 2 solar mass. The radius is about 10 kilometers. On the surface of neutron star, it has the largest magnetic field in our universe, from 10 to 10 Gauss to 10 to 15 Gauss. And the neutron star is covered by a large region of magnetic sphere. In the magnetic sphere, an amazing thing happens. The photon becomes massive due to the plasma effects. And in some region, the photon mass equals the light axion dark matter mass. We call it a resonant conversion region. In this region, the axion dark matter can efficiently convert to radio signals if the axion mass is very light, for example, order micro EV. And the radio signal can be detected by SK-like experiments. Almost all the detection of axion start from the Lagrangian, the interaction term of axion and the photon. Or in other words, the axion particle can convert to photon in external magnetic field or in electric field, and vice versa. And in the magnetic field of neutron star, photons becomes massive due to plasma effects in mass proportional to the electron density. And for the junior model, this electron density is determined by the period and the magnetic field distribution of the neutron star in the magnetic sphere. And we use, for simplicity, we use the dipole approximation for the magnetic field distribution, and it's very consistent with the observation. Thus, we have position-dependent photon mass, and in some region, photon mass equals the light axion dark matter mass. We call this region resonant conversion region. In this region, this axion photon conversion probability can greatly enhanced due to the resonant effects. Also here, we also require the adiabatic condition, the coherent condition, we need the resonant conversion. This is essential to observe the radio signal from the axion dark matter. We expect to observe line-like radio signals from the axion dark matter. The peak frequency is about the axion mass over 2 pi. For example, for 4 micro EV axion dark matter, the peak frequency is about 1 gigahertz. So for fast SK and GPT, they can cover the frequency range from 0.07 to 100 gigahertz. It corresponds to the axion mass from the 0.2 to 400 micro EV. Here we give a benchmark point which is consistent with the resonant conversion condition, adiabatic condition under the current axion search. Here, the typical signal is about 0.5 microjansky. We need to compare the signal with the sensitivity of the radio telescope. Here for SK1, 100 hours observation time gives about 0.48 microjansky. I think it's already to observe the signal. For SK2 with 100 hours observation, the sensitivity is about 0.016 microjansky. It's much lower than the signal. So we can, by this simple estimation, we can say that the SK can observe these radio signals converted from this very light axion dark matter. And this new approach has many uncertainties. For example, the dark matter density, the magnetic field distribution, the velocity dispersion, and the plasma effects. After our simple estimation, there are more and more dedicated studies. For example, here later by Ben James Sapri, and later, even in this paper, there are still many uncertainties until very recently. I think 2 months ago, this paper they have very precise study on this axion dark matter conversion to radio signal. If you are interested, you can refer to this paper. I did mention that this SK search for the very light axion dark matter becomes a hot topic and attract a lot of attention. For example, in this paper, the Europe Strategy for Particle Physics Update 2020, they included this new approach to search for axion dark matter by radio telescope. And this current review modern physics by this famous professor. He also included this new method of searching for axion particles. So far we only consider the diffuse axion particles. We know the axion is scalar particle, or boson. Boson particle can relatively easy to condense to Bose-Einstein condensate, like the axion cluster, and then further they can form the collapse and form the axion star. I recently, and my collaborator in Washington University, we extended the previous idea to and correlate the axion star with the mysterious fast-switch burst. We can use the resonant conversion of the dense axion star moving in the resonant conversion region to explain the non-repeating fast-switch burst. And his idea is similar, so I skip the details. I'll move to another fancy dark matter candidate, the dark photon dark matter. We generalized the previous idea to this dark photon dark matter case, and we have many new advantages compared to this axion dark matter case. This is based on my recent work with Haipeng, Janil, and Weixue. This is motivated by I think this work started early, motivated by the famous paper, I think about roughly 2 years ago, this very famous paper, they proposed some mechanics to explain the whole dark matter by very light dark photon. So we studied how to detect this very light dark photon dark matter by radio telescope, following the same idea as the axion dark matter case. This assumption is very simple, just assuming the dark photon has kinetical mixing with the photon. So for the dark photon dark matter, the conversion between the photon and dark photon doesn't need the magnetic field, so we can, and we know the flux density proportional to the distance square inverse. So the closer the source, the stronger the signal. So we consider the closest astrophysical object, we consider the sun. So we consider the resonant conversion of that photon, dark matter conversion to radio signal in the solar corolla. This solar corolla is difficult to see by eye. We can only see this solar corolla during a total solar eclipse by our naked eyes. For example, here this is a solar corolla. It has two advantages. One is the sun is much closer than the neutron star or any other pulsar, and the sun is very close. And the other advantage is the region of the radius of the sun is very large compared to neutron star or other or pulsar or magnetron. So the conversion volume is much larger than the conversion region in the neutron star. So we expect the signal is much stronger than the neutron star case. But they also have a disadvantage because the sun itself has a radio background. So we have stronger background. So we need to carefully include studying the backgrounds radios from the sun. So the basic picture is shown here. This is our sun, and the outer region is the solar corolla. In this region, there is electron plasma, and the photon get a effective plasma mass in this solar corolla. And the photon mass depends on the electron density, and in some region, the photon mass equals the dark photon dark matter mass. In this resonant conversion region, this dark photon can efficiently convert to the radio signals if the dark photon mass is very light, for example, lighter than order micro EV. So we can use the radio signal on Earth to detect this radio signal from the dark photon dark matter. This is the distribution of electron density and the corresponding effective dark photon mass at the surface of the sun. In example, in the solar corolla, this mass from 10 to micro EV to 10 to -37 EV. And then we need to calculate the production of the resonant production of the dark photon to radio signals. We can use two methods. One method is from the quantum field theory. The other, we can use the wave function approximation by solving the equation of motion. But finally, we obtain the same conversion probability using the two different approach details even in the supplementary material in our paper. Different to the neutron star case, we need to carefully study the absorption effects during the propagation when the radio signal propagate out of the solar corolla. We find that the dominant absorption process is the inverse Bremsstrahlung process. The last piece is compared with the minimal detectable flux density of the radio telescope. Generally, the minimal detectable flux density is quantified by this the system equivalent flux density and the observation time, the bandwidth. So the important point here, we need to include the background from the sun. This is a very strong background. Also need to include the noise from the galaxy and our universe. So combine the production rate, the propagation effects, and then the radio telescope sensitivity, we obtain the final constraints on this kinetic coupling for different dark photon mass. For example, this red region represents the expected sensitivity for SK1 with 1 hour observation time and 100-hour observation time. We can see that the sensitivity is much better than previous experiment, especially, for example, for the LOFA, for the lower frequency region. This LOFA 1 hour observation and the LOFA 100-hour observation is about 1 to 2 order improvement compared to the CMB constraints. And then in future, the SK2 the sensitivity is much higher than the SK1. So we expect in future, the sensitivity curve become lower and several orders, maybe below here. So we expect this radio telescope can provide the best probability to detect or constrain the light dark photon case. So now this is the last simple conclusion, or kind of taking home message. The SK-like radio telescope could provide new idea to explore the light dark matter. Thanks for your attention. Comments on the collaboration are welcome. Last, I need to give advertisement. Our center has many faculty position opening, so welcome to join us. Thank you.
Okay, thank you for nice talk. Okay, so we can have one or two questions. Yeah, is there any question?
Yeah.
In the meantime, anyway, I have one question. So, basically, you showed us your search limit based on SKA has some better sensitivity in around micro EV or sub micro EV vision compared to helioscope experiment. So that means this kind of search is also better than standard action-like particle search.
The action-like.
Yeah, action search. Yeah. As you know, there are lots of standard QCD action search experiment. So then SKA has better sensitivity compared to such standard action-like particle search.
For axon case, because axon for search for axon, we need the magnetic field is very large. So in this case, we need observing a neutron star or pulsar. So the distance is very far, so the signal is weak. This also, someone, I think recently there are many works to compare the which is better, the traditional search and the least fast. I think in this paper, if they are showing the dark matter density around the neutron star is very high, in this case, this measure is much better than all other action search. But this assumption is too strong. For example, here, I remember if they require the sensitivity is the best SK from SK, they assume the dark matter density is 10 to 14 in terms of local dark matter density. So it depends whether SK is better or weaker, depends on the environment, or more precisely on the dark matter density around the neutron star. So the higher the dark matter density, so the stronger constraint, the stronger of the constraints.
Okay, I see. So it's time to change the speaker. So no more question. Yeah, if not, let's thanks to again. Yeah, for the very nice talk.
Thank you.
And then let's move to next speaker. So next speaker is Motoko Fujiwara. So are you ready?
Yeah, can you hear me?
Yeah. So please prepare your slide, and full screen mode is better.
Let me see.
Yeah.
Yep. How about this?
Yeah, that's great. So next speaker is Motoko Fujiwara from Nagoya. She'll talk about a model of electrically interacting non-abelian vector document model. Yeah, please start.
Thank you for your introduction, and thank you for this opportunity to present to you today. My name is Motoko Fujiwara from Nagoya University. Today, I would like to talk about a model construction of electroweakly interacting non-abelian vector dark matter. Today's talk is based on this paper shown in JHEP, and here is my collaborators, Tomohiro Abe, 順次したの and 浩平松下。Then let me start from my introduction. Thanks to the Planck collaboration, we know the correct dark matter energy density in the current universe. So once we fix the attractive WIMP scenario, then what we have to do is to reach this canonical annihilation cross-section for the dark matter. At this moment, we do not specify the dark matter interaction with the ordinary matters, but let me put a simple assumption to explore dark matter physics today. That is, the dark matter is a SU2L multiplet. So we assume the interaction between dark matter and ordinary matter is electric interaction. And then the dark matter multiplet gauge charge is determined to realize the electrically neutral component. So we can perform the model study. And thanks to these people, we can read out the following general features. First is thermal abundance can be reached by the order 1/12 dark matter mass. The second, the mass splitting between charged component and dark matter neutral component tend to be order 100 MeV. And this is a quite general feature for electric multiplet dark matter because these features are determined only from the electric properties. So you might think there's nothing new to reveal, but please look at this column. These model studies are focused on only spin 0 and spin half dark matter scenario. So a naive question is, how about spin 1 dark matter? Can we construct a concrete model? Or what about the phenomenology? Or are there any differences from spin 0, spin half scenarios? Actually, we have several ways to explore the electrically interacting spin 1 dark matter. First, we can construct a dark matter model with this kind of spin 1 dark matter in the extra-dimensional setup. Second, of course, we can introduce this spin 1 dark matter as a matter contents. But let me take the third way, extending the gauge symmetry. Please remember that all the massive vector spectrum in the standard model is gauge bosons associated from the standard model gauge symmetry. So we can consider the naive guess. The new spin 1 dark matter might be a gauge boson from extended gauge symmetry. We also impose the dark matter should have non-abelian electric interactions to dominate dark matter physics from the electric property. But we have still non-trivial question. First, how can we realize electric interaction for new spin 1 spectrum? Second, how can we stabilize dark matter candidate with electric interaction? And lastly, how can we obtain the standard model spectrum in the low energy? To overcome these highly non-trivial questions, we came up with the following ideas. And here it is. We extend SU2L symmetry in the standard model into 3 direct products of SU2s. We also impose exchange symmetry between gauge groups. And you might think that our gauge symmetry structure seems ad hoc, but our idea is inspired from the method of deconstructing dimension. Using this method, we can realize a similar spectrum in the extra-dimensional theory from the renormalizable setup with many direct products of gauge groups. And finally, we can realize that this odd spin 1 spectrum, and at the same time, we can easily realize the standard model spectrum in the low energy. And let me introduce our model briefly. Here again, the gauge symmetry structure, we named SU20, SU21, SU22 for each SU2s. We also impose exchange symmetry between SU20 and SU22. And here is the matter contents. And for the fermion sector, we introduce the same particle contents as the standard model once we regard this SU21 to be SU2L in the standard model. For the scalar sector, we introduce 3 fields, phi1, phi2, and capital H. Phi1 and phi2 are bifundamental fields. Namely, phi1 is assigned to be the fundamental representation under SU20 and SU21. For phi 2, fundamental representation under SU21 and SU22. And here is the transformation law under our setup. First, exchange transformation under this symmetry is shown here. Namely, we exchange phi 1 and phi 2, and at the same time, W0 and W2 are exchanged, which W0 and W2 are the gauge bosons for exchanged SU2 groups. For the gauge transformation, we show the transformation law for the Higgs sector. At this moment, you might think that where is the SU2L and where is the Z2 parity to stabilize dark matter candidate? And to answer these questions, let me show briefly detail about the symmetry breaking structure in our model using this slide. In the sufficient high energy, we have the extended gauge symmetry as shown here. And in the low energy, we only have U1 element symmetry. To realize this symmetry breaking, we assume the following wave for Higgs fields. Namely, we assume diagonal wave, the same diagonal wave, which is characterized by V phi for phi 1 and phi 2 fields, and lower component wave for capital H. From the phenomenological issue, we assume the following hierarchy between these two waves. So the first part of the phase transition is occurred by these phi fields wave. And we can find these waves are invariant under the gauge transformation with the same mixing angle for these SU2. In this sense, the generators of SU20, SU21, and SU22 are identified. So we only have only one SU2 symmetry after this breaking. So we can regard this SU2 symmetry to be SU2L symmetry in the standard model approximately. And second, we also have exchange symmetry because we assume the same wave for phi 1 and phi 2 fields. The remaining story for the symmetry breaking is almost the same as the standard model one because we have already found the SU2L cross U1 hypercharge structure. And after all these symmetry breaking, exchange symmetry is still alive. And in the next slide, I will show we can find the Z2 parity structure from this exchange symmetry. Then let me explain about the detail. After the symmetry breaking, we use the following scalar field definition. And we only have 3 neutral scalars as a physical degrees of freedom, which is sigma 1, sigma 2, and sigma 3. And exchange symmetry transformation law can be shown here. And let's consider the exchange transformation law for neutral scalars. For the latter convenience, we'll take the following basis. And here is the transformation law. From this expression, we can read out the Z2 parity assignment for each scalar states. And moreover, we can find this Z2 odd state is automatically physical state because we have no mass mixing term due to this exact exchange symmetry after SSB. For the Z2 even states, we do have mixing with angle phi h. So we have small h and small h prime as our physical states. And small h is a 125 GeV Higgs in our setup. Then let me summarize the point of this slide. We impose exchange symmetry between SU20 and SU22 as a stage of the model construction. And this is nothing but the Z2 parity assignment for physical states as shown in this slide. And we have the same story in the vector sector. And so we can find the Z2 odd vectors V0 neutral scalar and neutral vector, V plus minus charge vector. To focus on the spin-1 dark matter scenario, we assume the following mass relation. And so V0 is our spin-1 dark matter candidate. And we can find the SU2L triplet-like features between V0 and V plus minus. For example, these tree-level mass are degenerated with each other, but this degeneracy is broken by the electric radiative corrections. And here is the mass spectrum after the symmetry breaking. And here is the these odd states. And this upper box shows the BSM spectrum. And we find all these BSM mass are proportional to only one wave, V5. So we can find the standard model limit very easily. That is, V5 goes to infinity. So we can realize the standard model spectrum very easily. And we also find, and our spectrum contains G prime and W prime. So we can expect corridor search is viable to prove our dark matter model. So let me show our result in dark matter mass and G prime mass plane. Here is the phi h contours, and we determine the value of phi h to realize the correct dark matter energy density. In this white region, we can realize the correct dark matter energy density by tuning the value of phi h. Because we have the Higgs exchange channel in addition to the electric channels. But even if we switch off these Higgs channels, we have the plenty of electric channels. So on this blue boundary, we can achieve the correct dark matter energy density only through the electric channels. So in this sense, we can call our dark matter model as electroweakly interacting spin-one dark matter model. So the next question is, what's the constraint on this plane? And here is the last figure in my talk. And we are focusing on this region in the previous slide. And again, dark matter mass and G prime mass. And yes, we do have the strong constraint from the perturbative unitarity bound in the Higgs, in the scalar scattering, which is shown as a purple shaded region. So our viable region is this white narrow region. And we further find we can prove this viable region in the next generation direct detection experiment, such as XenoNT experiment, because we have the scattering channel as shown here. But please note that the degeneracy of the contour at this boundary, we can realize the thermal abundance, correct thermal abundance only through the electric channel. So we can switch off phi h. Then we do not have the direct detection bound. In that case, we can make use of the double prime search, because double prime search channel is nothing to do with the Higgs mixing angle. So we can prove this region even if we switch off the Higgs mixing angle totally. Then let me summarize my talk. Today, I consider the non-abelian extension of the electric symmetry, as shown here, and impose exchange symmetry between two-way CO2s. Finally, we can realize these odd vectors and find the stable dark matter candidate with spin 1. And this dark matter has non-abelian electric couplings, so we can dominate the dark matter physics only through the electric interactions. And finally, we show our numerical results and find the viable region. We also find that this viable region can be tested in the future next generation direct detection experiments, such as XenoNT experiment and double prime search in the high-level HC, as shown here. That's it. Thank you.
Okay, thank you for the nice talk. And yeah, you keep the time quite precisely. So we have some time for question. Is there any question? So if you have a question, you can raise your hand, or you can turn on your microphone. No question. Okay. Okay. Yeah. Then I have one question. So basically, yeah, your one is one of the vector dark matter model. So as you know, there are some other vector dark model that already exist and suggested. So do you think which one is the characteristic feature of your model compared to other vector dark matter model?
So your question is outstanding features of a model, right?
Oh, yeah. Why? What is a special feature of your vector dark matter model compared to existing other dark matter model?
I see. Thank you. Very good question. And for the short answer, the non-abelian electric couplings of our spin-on dark matter, because we can construct say dark photon portal model or some other kinetic mixing portal model, but our vector dark matter has non-abelian electric couplings, so which realize plenty of electric channels to annihilate dark matter in the early universe. So we can realize correct dark matter density only through the electric channels. I think that is this is the most outstanding features in your model.
Then mostly you just discuss collide search and document directed search. So how about indirected detection?
That is also a very good question. And actually, that question is involving to our next future collaboration. Let me explain using this backup slide. And what we found in this current search is dark matter mass should be much heavier than the electric scale. And that means the Zohmer effect and enhancement effect in the annihilation process should be viable. So we have to consider the non-perturbative effect to calculate the precise prediction for the annihilation rate. So we are planning to publish a paper in arXiv maybe in next month. So I'm very happy to looking forward our new paper.
Okay, thank you. So no more question. So then let's wrap up this talk here. Lessons to the speaker again, and then then move on to the last speaker of this session. The last speaker of this session is Manoranjan Dutta. So are you ready?
Yes, can you explain?
Oh,
yes, yeah.
So
is my screen visible?
Yeah, good.
Okay.
So,
I thank the organizers. Yes.
Yeah. The last speaker is Manoranjan Dutta from IIT in India. So he'll talk about self-interacting inelastic dark matter in the light of Gen 1 to access. Yeah, please start.
Yes, thank you. And I really thank the organizers for giving me this opportunity to present our work on self-interacting inelastic dark matter in the light of Gen 1 to access, which was done in collaboration with Satyabhata Mahapatra, Debasis Bora, and Narendra Sahu, and was recently published in PRD. So the story begins with this. As you all know, the standard model of cosmology, or the lambda CDM, where lambda stands for the cosmological constant or dark energy, and CDM refers to the cold dark matter. It enjoys a wide range of observational success and evidence for cold dark matter coming from gravitational lensing, from the galaxy rotation curves, bullet cluster, and CMB, as already stated by Mr. Wang in his talk. However, at small scales, there are certain issues with lambda CDM. The most prominent problem, which is known as the cusp score problem, is that while lambda CDM predicts a cusp profile with central halo density varying as R to the power -1 or -1.5, while the observation suggests a core profile with constant halo density. Another example is the missing satellite problem, where lambda CDM simulations predict much more satellite galaxies than those being observed. And while one may say that maybe there are such satellite halos, but they have stripped their stars off in some gravitational collisions, but which leads to another problem, which is known as the too big to fail problem, where some of the predicted satellite galaxies, satellite halos, are just too massive that it is so unlikely that they do not have visible stars. So while these issues associated with the lambda CDM can be explained, can be addressed from the baryonic feedback mechanism, a promising alternative was proposed around 2000 by Speisel and Steinhardt, where they have abandoned the cold and collisionless nature of the dark matter, and they have said that dark matter can have sufficient self-interactions among themselves so that the particles will get scattered out of the dense halo, giving us a core profile as that's been observed. And since there is now less enclosed mass, so rotation curve will be reduced and the simulated satellite will match to the observation. However, we have an enormous range of structures in our cosmos, right, starting from the dwarf galaxies up to the cluster of galaxies. And while stronger self-interaction is favored by the dwarf galaxies in order to address these issues, which have typical velocity 10 km per second, the large structures with typical, like a cluster of galaxies with typical velocity 1000 km per second, favors a weaker self-scattering. So a constant self-interacting cross-section across all the scales won't help us. We need a velocity-dependent dark matter self-scattering so that at small scales, the self-interaction modifies the physics, but at large scale, the lambda CDM predictions retains. So in analogous to the strong interactions mediated by pions, we can have a light mediator well below the weak gauge boson and much lighter than the dark matter so that we can have a velocity-dependent cross-section. Now, dark matter with a light mediator has also received serious attention when last year in June, the Xenon-Wanton collaboration reported an excess of electron recoil events in the recoil energy range 1 to 7 keV, peaked around 2.3 keV, which precisely sets the platform for our work. That is, we wanted to ask the question, can a self-interacting dark matter with a light mediator also give rise to the reported Xenon-Wanton excess? To address this question, we proceed in a model building approach, where we extend the standard model of particle physics by a vector-like fermionic singlet, both charged under an additional U1 symmetry. And while the scalar phi Aquarius wave, it not only breaks the U1 symmetry, but splits this Dirac-Farman psi into two pseudo-Dirac states, psi1 and psi2, with a mass difference delta m between them, which we kept equal to 2 keV in order to explain Xenon-Wanton axis. And the light mediator Z prime associated with the U1 symmetry will act as the light mediator for the self-interaction. So these are the Feynman diagrams responsible for the self-interaction. And ignoring this term, due to the suppression by the heavy mass scale m, we can write down the potential, the effective potential. This is a low energy phenomena at the current universe, so we have to solve the Schrodinger equation. And we show the result for the clusters, the self-interaction in clusters. So the top left panels gives the elastic scattering in the ground state. The top right panel gives the elastic scattering in the excited state, that is psi to psi2 going to psi to psi2. The bottom left gives the upscattering from psi1 to psi to psi2 in clusters. And this bottom right panel gives the downscattering, that is psi to psi2 going to psi1. And we restrict the self-interaction from 0.1 to 1 gram for clusters with typical velocity 1000 km per second. In galaxies, we allowed somewhat more, 1 order of magnitude more self-interaction, up to 10 centimeters square per gram. And again, we vary by keeping the gauge charge G prime of U1X symmetry at 0.1. We vary the dark matter mass in the y-axis from 0.1 GeV to 100 GeV, and the Z prime mass from 5 into 10 to the minus 4 GeV up to 0.1 GeV. And then we come to the dwarf scales, which have very small velocity compared to the galaxies and the clusters. So they do not, the particles in the ground state do not have sufficient energy in order to upscatter. So the upscattering is missing here. Only the elastic scattering in the ground and excited, and the inelastic downscattering is possible in case of dwarfs with typical velocity 10 km per second. So again, here we allowed the cross-section to be 1 order of magnitude more, up to 100 centimeters square per gram, as depicted by the color codes. And we have also achieved the required velocity dependence in the cross-section. Here we saw the cross-section per unit dark matter mass as a function of the velocity, and the value and the obtained result has been fitted to the observed data. So as you can see, as the velocity increases, the cross-section decreases in order to match with the lambda CDM predictions. So coming to the dark matter relic density issue. So these are the two Feynman diagrams that will decide the thermal relic of the dark matter. The point which is allowed by the self-interaction, we have taken 1 GeV dark matter with 10 MeV Z prime, and we have keep this kinetic mixing epsilon very, very small, of the order of 10⁻⁸, which is again in order to explain the xenon one-to axis. However, due to too much annihilation into light Z prime coming from the left-hand side plot, the thermal relic is underabundant by almost 3 orders of magnitude. So we need to go for non-thermal production of dark matter. And however, the dark sector thermalizes within itself. And the process, the dark matter electron going to dark matter electron, which is depicted by this dashed magenta line, brings the dark sector into thermal equilibrium for a very short period of time. And that is why, while solving the couple-Boltzmann equation, we separate the parameter space into 2 regions. One is up to where we define X as the dark matter mass divided by the temperature of the universe, and up to X less than 0.03, they were kinetic equilibrium. Both the dark sector and thermal and the standard model sector shares the same temperature. And from 0.03 up to 100, 100 is when all the dark matter particles become non-relativistic. But between these 2 points, the dark sector temperature, which is we denote as T prime, evolve as the ratios of the relativistic degrees of freedom of both the sectors raised to 1/3. However, in order to rescue the relic up to the correct ballpark, we have to introduce another scalar eta, which can decay in late times into the dark matter particles, thereby pulling the relic back to the correct. A couple will be clarified. So result of those equations, the y-axis we have shown L y as a function of x. So this blue dashed line gives us the production of dark matter from chart. But it is a freezing production, and which will be quickly annihilated into Z prime again, and giving us much underabundance. That's where the scalar plays its role. It will first thermal freeze out and then decay, thereby pulling the relic back to the correct ballpark. So as you can see from the right-hand side plot, that the fractional contribution of both the dark matters are almost equal due to this very small mass splitting between them. Coming to the xenon one-to axis, which can be explained by the inelastic downscattering of the dark matter with the electrons of the xenon atoms in a detector mediated by the Z prime mixing, which we fix at 4 × 10⁻⁸. And for dark matter mass 1 GeV and delta M 2 keV with Maxwellian distribution of velocity with most probable velocity 1 × 10⁻⁻3, we have obtained a cross-section of the order of 10⁻⁷ GeV-2. So here we saw the event rate as a function of the recoil energy of the electron, and we for the parameter space specified a nice fit, taking into consideration the detector resolution, the velocity distribution, and atomic excitation factor, where NT is the detector mass density, which is 4 × 10⁻27 ton inverse, and A is the Bohr's radius, and M is the mass of the electron. So this kind of peak is a characteristics of the inelastic dark matter models. That is, whenever the recoil energy of the electron is of the order of the mass difference delta M of the 2 states, that's where the maximum momentum transfer occurs and we get a peak. So finally, we confront our model to all the relevant theoretical and experimental constraints available for the parameter space of Z prime and MZ prime for our model. Nearly half of the parameter space denoted by the sky blue line has been ruled out from the demand that the light mediator Z prime should annihilate into, so to decay into the neutrinos before neutron decoupling happens in order to avoid the entropy injection. And in the top side, this yellow squared portion has been ruled out by demanding that the dark matter freeze out should happen before Big Bang nucleosynthesis. And this triangular region of the pink color has been ruled out by demanding that the dark matter, the excited state, that is psi2, which can in principle decay to psi1 and a couple of neutrinos, should have a lifetime which is of the order of the age of the universe. and this green spikes has been ruled out due to insufficient self-interactions in those regions. So leaving only this white area as the allowed region. However, Zenon-Wanton favors only this blue patch. So giving us only this tiny parameter space in the Z prime and MZ prime plan, which is simultaneously allowed from direct this Zenon-Wanton axis and relic density as well as self-interactions, making the model very predictive, which can be verified or falsified with upcoming data from Zenon-Anton or other recoil experiments in the near future. So, and there are some portions which have been ruled out from the other ongoing direct search experiments like Lux, Crescent, and News, etc. So we have achieved the self-interactions by postulating, by extending the standard model minimally. And we have also explained the Zenon-Wanton axis. So we have built a model which is very predictive, which can be verified with new data coming from the future experiments. So that's all. Thank you very much.
Okay, yeah, thank you for the nice talk. So yeah, we have enough time for the questions. So yeah, if any question, raise your hand, or yeah, you can turn on your microphone. So is there any question?
May I ask a question?
Yes,
Yeah,
please.
Please.
Okay. Yeah. First of all, thank you very much for your interesting talk. I just have one question about the Rayleigh abundance of the excited state. So it seems that it's very important to keep the abundance fraction of the excited state until the present universe. And I just wonder until when the chemical equilibrium between the excited state and the de-excited state is kept. So the reason I'm asking this is that this chemical decoupling point is important to determine the Rayleigh abundance ratio between them.
Yes, sure. Yeah. So the dark sector, dark sector maintains its equilibrium up till the up till the present universe, actually, because it can their temperature after the T prime, which evolves up to x equal to 100, and whatever temperature they have at x equal to 100, they just retain it up till now.
Yeah, so basically the interactions cross-section between the excited state and the de-excited state is very strong, right?
Yes, right, very right, yeah.
So I just wonder how the chemical interaction between them decouple around x equal 100. So I just naively imagine that is the chemical equilibrium is kept beyond x equal 100. So for example, if we have a look at the previous plot, maybe a previous slide.
Yeah.
The slide that shows the abundance ratio of the excited state and the de-excited state. Yeah. Okay. So they chemically decouple around x equal 100 somewhere between x equal 100 and 1000.
Yeah. Right.
So they decouple just about when the exponential suppression, exponential difference between the abundance ratio starts to come in, right? Am I understanding this correctly? So so from this figure, I think that maybe the decoupling point, the abundance ratio between them is exponentially sensitive to the decoupling point.
Yeah, but we have to keep in mind that if you look at the scale, the y-axis, although the figure looks it's very exaggerated, but actually they are equally abundant. This is just 0.5005 and this is just 0.49999. So they are almost equally abundant in the universe as well.
Yes, right. So this is actually what I'm wondering. So it looks like they have very similar abundance ratio, but I think that if this equilibrium is prolonged a bit more, then the abundance ratio would be exponentially suppressed, I think. So this means I think this decoupling point really determines the abundance ratio, and it's really crucial for this model. In this model, it's really crucial to realize the early decoupling. And I wonder if it's really natural to realize such a case, to realize the early decoupling between the excited state and the ground state.
Yeah, this is, I mean, this point here in this work, this point is very sensitive to the, the parameter space that we have taken for the couplings. We have, implemented the model. So it is very much sensitive to the, for example, the Z prime coupling and the mediate Z prime mass. Only for those specified value we have obtained this plot. It is, this point is not a general statement.
I see. I see. Thank you very much.
Okay. Then, is there any other question? I cannot find anyone. Okay.
I have a question.
Oh, yeah. Yeah, please.
So I think related to the previous question by Hee-jun. My question is about kinetic decoupling temperature in your model. What is the kinetic decoupling temperature? Because you have a mass splitting, which is about 2 keV. So I think the abundance of the heavier component strongly depends on the kinetic decoupling temperature. So I can model by model, but sometimes it's hard to realize it. So what is the kinetic decoupling temperature in your model?
Kinetic decoupling occurs somewhere. If you look at this red line gives the Hubble line. So if we look at the DM electron and DM electron interactions, this magenta line. So it is somewhere like around 0.03 where the dark sector decouples. Somewhere in this point. If it is visible from that side, X is defined as dark matter multiplied by the temperature of the universe. So for 1 GeV dark matter, and we have obtained X equal to 0.03.
What is temperature then? I cannot see where. So X is small.
X is 0.03, M is 1 GeV. So
1 GeV.
Yeah. So 1 divided by 0.03.
I see. Okay.
Oh, yeah. It's time for the end of this session. So yeah, if you have no more questions, you can wrap up this session here.
Maybe if we can discuss off the meeting also. So.
Okay, thank you. Thank you for the nice talk, and thank you to all of the speakers of this session. It's very, very nice. We can keep the planned schedule. Thank you, and see you in break time, and then we can see next session. Thank you.
Yeah, thank you.